So first of all, James, thanks for the invitation here, and I want to really highlight after working out that this work was very heavily done by Josephine, who gave a talk the other day. So now, which one is forward? That one. So the question is, if we want to start thinking about energy transport, we need to start thinking about different ways of doing it, and quantum engineering has kind of allowed us to now start engineering our reservoirs. So the question is, if we want to move energy, there's always going to be a trade-off between efficiency and speed. So we know that some of the faster quantum processes are associated with super radiance, super transfer, and various things like this. So the idea for motivated this work was just, what can we do? And what's interesting fundamental science? So I can say there's almost no experimental demonstrations of this stuff, apart from some work we did with colleagues in Vienna a few years ago, and this was taking a hybrid system, basically a superconducting resonator with an NV ensemble in it, and just trying to see, in this all-solid-state system, can we see superradiance? And one of the keys for superradiance, and it's one thing that I want to mention straight up, superradiance is not a quantum phenomena. It is a semi-classical phenomena. Standard rate equations predict everything you want to see. But the question is, if you want to start thinking about superradiance, you have to show an n-squared dependence, but there's also the time, the time scales as the ensemble size comes up. It scales as the emission time is 1 over n log n. But the question in diamond is, we have a particularly bad problem, okay? We get a nice chunk of diamond. How many NV centers are in it? Well, yeah, 10 to the 18 plus or minus 40 or 50% or something like this. So how can I controllably change that number? So the idea in this case was that luckily NV has 4 orientations. So we may not know n, but I can change the orientation of magnetic fields through the diamond that I couple to and go from n to 2n to 3n to 4n. And if you do this, what you see first of all is that from the resonator itself, you see a nice emission of pulses. You see a nice emission here, and that's telling you what's happening from the cavity mode. But the tricky part in this experiment was we also want to know what's happening in the diamond itself. And while this data could be seen on, you can do the whole experiment in a few seconds. If you want to actually measure the diamond and build up enough statistics, this took 6 months, and that's why the error bars are so high. But we can see the typical Tanch kind of curve that you see for the population from a series of emitters. You can change the size, the number of NVs coupled. You can plot it. You don't get n squared. You get something like n to the 1.5. We used a different diamond. We then got an n to the 1.4. And this is just due to partly strong coupling, partly we have dephasing in the system. But the thing I want to mention that's important in this case, given that we're working at cryogenic temperatures, we know the T1 of our NV centers is about 40,000 seconds. We know the T2 is roughly 1 microsecond. So you can kind of tell here that to get light out in around 300 nanoseconds, we're coupling here about 10 to the 12 NV centers. Can we only see superradiance in solid-state systems like this? Are there other kind of systems that we can use to kind of see this? And the answer obviously is yes. And this was a kind of provocative one from some experiments a few years ago. And you can actually, and I'll be very careful with my terminology here, you cannot see, but you can infer superradiance in these double domain nuclear spin ensembles that are present in gallium arsenide semiconductors with Nambu-Goldstein modes. The reason we can't, we can see that in this double domain, we can see, we can measure the timescales of milliseconds, but we can't measure the very short time scale, but the entire dynamics, you can't explain the particular dynamics without having a superradiant decay in this. And I mean, it was kind of surprising that something that's very thermalized, you would still see something like this. But the interesting reason that I brought this up was the NV was kind of a one spin ensemble. This one is a double nuclear domain, so it's kind of like two spin ensembles with the same one. And if we start thinking about two spin ensembles, we can start thinking about a system A, a system B. I'm now going to couple this to a reservoir, a resonator. We're both coupled equally, so I can't distinguish if the emission was from one resonator or another. And if you do this, what you find out is if you excite the first ensemble, have the second one in the ground state, you see this superradiantly decay, theoretically. You see ensemble B that was in its ground state, superabsorb. And it will stay, if you think about the NV diamond kind of experiments, it will stay at this kind of regime in this pseudo steady state, 40,000 seconds, for a long, long time. Is it a negative temperature? Obviously not. But the sheer fact is when you look at an individual system, it stays in this excited state for a huge amount of time. So why is this happening? We first need to think about how we're actually modelling this reservoir at the moment. And the simplest way is just to use collective spins, and you have this Lindbladian term, a JA plus a JB. But what's the explanation? Why is it doing this? And the simplest thing to think about is what's actually happening. So think about just the simplest possibility. Spin system A has one spin up, spin system B has one spin down. Mathematically, just as a simple trick, I could rewrite this as the triplet state plus the singlet state. If you add those two together, you get this. But then when you think about what this dissipator does, this triplet state decays to the ground state. This here is a dark state. The dark state is immune to this. So therefore, what happens is this state, by just action of the dissipator itself, decays to a mixture of the ground state and a triplet state. And as you increase the number of spins in system A, the number of terms in the ground state goes down, and you end up moving to a system where where the second system is always in this excited state. So this is kind of interesting. Symmetry is here important. So let's just come through and show a few more plots of this. So the previous slide showed two, but I can think of having one here with the reservoir, another one here with the reservoir, another one, and if you just start with the simple ones, 40 spins in one, 2 in the other, and here I'm normalizing by the number of spins just so that the plots stay roughly the same. Superradiant decay, superabsorption, not quite fully excited. That's 2. When you go to 3, down, the second one comes up, then the third one comes up, and then you can go to 4 and 5. And this thing means that you're moving energy on. The interesting thing in these plots really is that this time scale here that this is happening roughly on your 1 over n log n kind of time scales. Of course, this is idealized. And as a theorist, I like idealized systems. What happens as we start saying, okay, it's not a zero temperature bath, and you can add thermalization in, and what you see is what thermalization does is it means that your system decays faster, but you don't reach the same efficiency, you don't go up as high. These are very small system sizes, so as we make life bigger, so consider now a system with 3, 1, 10 to the 6, 10 to the 4, 10 to the 2, and you see very nice, sharp transitions where system 1 migrates energy, or whatever terminology you want to use. System energy leaves system 1, appears in system 2. It stays there for a period of time. Then it moves to 3, and as you increase the system size, these regions become even more pronounced. So it's kind of like energy here, appears here, appears here. Is energy moving? That's a debate we can have because basically there's no direct transport of energy, but there is a virtual process kind of going on. But the key here is that suddenly what you notice is the timescales here are getting very, very short. As the spin size goes up, previously we were around 0.1, here we're now at 10 to the minus 5, now at 10 to the minus 7. This is getting even faster. Is that all we can do? It's energy. It's not quantum energy. Sorry, James. That's just energy migration. Can we do something with quantum correlations? And I want to make one point here, okay? And I'll skip back one slide or two. Is this classical or is this quantum? Super radiance by itself, I said, is semi-classical. Super absorption is semi-classical. If you combine both processes together, what you find is that there is a limited amount of entanglement in this. So can we do something else? Can we start thinking about quantum correlations? Can we move these ways? And the answer is obviously yes, otherwise I wouldn't be talking about it. So consider that you have system B in this case, a number spins up, system A and C spins down. You have this collective dissipator here and here. And I want to ask, how much entanglement do I end up in A and C at the end? What you notice here is that as the time goes on, system A and C become entangled. And as you increase N, the entanglement goes up, and it goes up to roughly 1/3. And what's interesting is, and we plot it down here, we plot it in the plot below it, is that the entanglement goes up. As the spin size goes up for B, it becomes faster for that process to actually happen. So you're creating entanglement at a faster rate. Do we only have to have A, B, and C? No, as I show over here, you can do similar systems where you can have A, B, C, D, E, F, and you can gradually move energy across. So that's bipartite entanglement. There's more in quantum mechanics than bipartite. Can I do tripartite? And the answer obviously is, if you think about system A, B, C, and D, I mean, the simplest way is if I have system A, B, and C all collectively coupling to D as one, then this is very like the battery ideas, and you can create entanglement that way. But we want to restrict ourselves to the case where we actually have just these pairwise dissipators, and what you see is that you can generate tripartite entanglement. If you go to 4, you can make 4-party entanglement. It does get smaller as you go up, but it's kind of interesting in a sense. So let me just see how much time. Okay, I'm still on time. So the question is that it, or is there other stuff that we can do here? Here I've been looking at the dissipators. What I can start thinking about now is in these transport problems, the dissipators are kind of a way of creating spatial correlations. But of course, I can go non-Markovian. And I can also change the form of the correlations. And what we found a number of years ago is that if you allow both spatial and temporal correlation and temporal correlation so that you're definitely non-Markovian, you can actually even enhance from the uncorrelated regime, the spatial correlations enhances by about 40%. So there's a whole series of gains that you don't want to be restricted to Markovian, exploit or engineer in really whatever correlations you can to the system and see how they work. Given that some of the earlier talks in the week, no problem. I put this slide in at the last minute, and this is just some previous work that as we get these bigger and bigger processes and various things like this, we've got to start thinking about how we get information out. And so this was experimental work we did with Xiaobo Zhu, one of my long-term colleagues in China. And the answer is very simple, okay? I'm going to give you either an ergodic state or a localized state of matter on the 61 qubit processor that they had. I want you to tell me which one it is. But I'm going to be mean, okay? Because everyone knows Bill is evil. I'm not even going to tell you what the 0 and 1 basis is. So 0 and 1 could be this way, 0 and 1 could be this way. I'm not going to tell you that. That's an extra piece of information, okay? I will say everything's the same, but I'm not going to tell you which particular one. And so the question is, can we use these NIST processes currently with machine learning techniques to actually start distinguishing between the two? So here I just plot the case is if you did nothing, okay, you see here your localized state, this is the ergodic state, and here's an overlap, but can we do better than this distribution? And the idea was, again, the initial idea was, okay, and those of you that have worked is asking someone to do 61 qubit quantum tomography is nasty. The problem in this system is that we have 61 qubits. If you're sensible, you'll use 2 or 3 excitations, correct? You'll keep yourself in the small excitation space. Boring. Okay, 61 qubits. Why don't they have 30 excitations? So make the experimentalist life difficult. But what you find out is that with the tech efficiencies of 96, 97%, I'm going to measure every qubit, 0.97 to the power of 61, I think is almost 0. So the question that Kainomoto and myself set the experimentalists was, okay, I'm just asking a simple binary question. Is it ergodic or not? And so I only want to measure 1 qubit. That's it. And what you can find is that if you measure 1 qubit, this distribution here, for a 4x4 system, you separate these two out. 5x5, you separate them well. 7x7, 8x8, there's even more. Why is this coming to the center? This is basically the larger size chips. We're starting to see it's longer processing time, seeing the phasing on the system. But maybe I'm cheating, okay? Because Bill does cheat, okay? Maybe I'm being very lucky that the particular qubit that I'm measuring actually has that information. So basically, we have to do honest experiments. So the question is, okay, let's take let's just take a simple 9-qubit system, take one of the qubits in the middle, and it's not part of this ergodic localized state. But this qubit 5 is going to be the one that you measure, and you still see the same distinguishing of state. So one of the take-home messages is when you're starting to think about these machine learning techniques, especially on these NIST processes and various things like this, think about the information you want and measure the minimal amount. If you can get away with measuring 1 qubit, so this experiment, I think it was a run that took about 4 hours overnight. When we were starting to try and do 61 qubit tomography, we estimated it was going to be longer than the lifetime of the PhD student. And there I'll be ambiguous. I mean, maybe, am I saying the PhD student is a PhD student, or am I saying longer than his actual lifetime? And there's an ambiguity here. So just to summarize, I mean, given that we can engineer these quantum systems now, we can actually think about new ways of moving energy. There is a trade-off that people have talked about here is how fast do I want to move energy? Efficiency versus trade-off. This dissipated scheme that I'd say, it's very inefficient for energy, but it's very fast. Thank you very much.
Thanks, Bill. Do you have any questions?
Thanks, Bill. I couldn't quite see what you were, in that last slide, what you were feeding back on to do the optimization. It was a bit blurry.
Yeah, so
Are they single qubit gates or what are they?
Yeah, so what happened is we had so after we had measured the thing, we had a rotation angle on every qubit that we could we could rotate so we'd create the exotic state, we'd put an arbitrary rotation angle on that would vary. Yep. And then basically we would then reverse the dynamics, and then we can put another rotation angle on. I can show you the plots afterwards,
Okay.
but
All right, thanks.
but it's basically a 2-parameter per qubit family.
Yeah, great talk and insight, Bill. Got a question. It was one of your early slides.
Yeah.
I didn't get a chance to clearly read it, but I think it was showing that when you daisy chain your ensemble,
Yeah.
the amount of energy transferred from the first ensemble to the last one decreased, but the time it took to transfer the energy actually decreased as well. Was that right from that plot?
So what happens is that it's basically, and when we got to the big ensembles, you can think about system A transfers to B in roughly the time associated with that large ensemble. Once it's in system B, then the time to transfer from system B to system C is really proportional to the size of system B now, not system A. So the energy it's still a super-radiant decay at every step. This is kind of a pairwise pop.
Just in the plot you had A to B, and on one plot, that was A, B, C, D
Yeah,
or something.
but it went A to B,
Yeah,
B to C,
yeah.
C to D, and it's basically
Yeah.
pairwise.
Yeah, but the plot
popping.
showed that from A to B took longer than from A to D.
Yeah, no, we were always. No, so basically,
Can
it was
you bring
A
up
to
the
B.
plot again? No.
Yeah, well, I can
Okay.
show you in the
Yeah.
slides when I can bring the slides back up. So
Yeah, okay.
Okay. Oh, one more question.
Hello. Yeah. So I think it was more or less the same question. I'm troubled to understand the coupling mechanisms. These are channels that you couple between the ensembles that are inside bad cavities.
they don't have to be cavities; they are reservoirs in a sense. So basically, when we thought about the NV, and one of the experiments that we're playing with at the moment is we put 2 NV centers into a bad cavity. That's one way of doing it. But for this semiconductor stuff, basically this is a semiconductor reservoir in a sense, heat bath in a sense.
So the photons, they are never traveling somewhere.
They're never traveling. I mean, they may move. The diamonds are not sitting on top of each other, for instance. They are adjacent, and there can be a gap in them. The question is, in the microwave regime, that 1 millimeter distance between the two suddenly means if I have a micron here and a micron here, I can have a few microns distance in between, so that the ensembles are not touching in a sense, experimentally.
And how do you choose to couple first A and B and then B and C and stuff? What do you switch on and off?
So in this particular case, the interactions are always on. The question really is to start with is how you excite the first ensemble. So once ensemble A, typically in the diamond thing, we would take that ensemble off resonance, then do a pi pulse on the ensemble or something approximate to it, bring it back into resonance with the cavity and the other ensembles, and then basically these interactions are always on. We're not turning the dissipators on and off.
Okay, so it's like a wave that is propagating.
yeah,
Okay,
exactly.
thank you.